All right, hello everybody. So Mark asked me to say a few words about the language roadmap, and I can't just say a few words, it's not in my character, but I'll try not to say all the words. The goal of giving this talk here today is not so much to say, hey, look at the 7 cool language features we're working on, but more to talk about what are the things that we have decided are important enough, at least for us to put effort on, that we think are important. And the reason for that, the reason to do this talk at all in this forum is that people often come to us and say, well, I want to get involved, but I don't even know what you guys are working on. And I certainly don't, I want to get involved in something that is important and that people are engaged in, but what are all of those things? So part of the point is to fill out at least some of the things that we're working on and or intend to be working on in the language area because we think they're important. And the reason we think these things are important are because we talk to customers, we talk to users, we go to conferences, we talk to professors, we talk to people and hear their pain points. And we listen to the pain points, we turn them over in our heads, and at some point plans emerge for, oh, we could address that problem with this feature or with this set of features. And so the process is a fairly diffuse one. It involves a lot of listening and turning things over and coming up with candidate solutions, the first of which is always bad, and the second of which is often always not so good. And by the time you get to the 5th or 6th iteration, you have something that might look like it actually belongs in the language. So I'm going to fill out a few of the things that we're working on in various stages. So you've seen this. As Mark said, we've been around for a long time. We've been declared dead many times over, and we've managed to confound those predictions. And what's the secret to doing that? Well, it's fairly simple. Stay relevant to the problems people want to solve, stay relevant to the hardware people want to run on, and don't break your promises, right? Compatibility, the commitment to compatibility is about not breaking promises. We told you this code would run. It's going to continue to run. In the last couple of years, there's been a shift in the way that we evolve the platform, which I think has been an extremely positive one, which is a higher degree of coevolution between the language and the JVM, and I think that's been incredibly successful. As Mark said, we have some principles here to guide us. I won't repeat everything he said, but readability is the most important thing. Readability, simplicity, and transparency. The takeaway is it should be easy to look at code and know exactly what it does, because that's code that's maintainable. That's code that you're not going to be wanting to throw away, and so that's code that you can maintain your investment in. Successful code lasts a long time. It's written once and it's read many times. In some other communities, the culture is no code lasts longer than 6 months. That's not the culture in the Java community. That's not what people do with Java. And we've aimed the platform, I think successfully, at building successful long-lived code rather than just banging out disposable code. And we make stewardship decisions accordingly. Evolving the language was always in the intention, but conservatively. Rather than try to guess the future, rather than try to follow fashion, we take a more conservative approach and focus on what are the real-world problems and pain points that developers face. And the answer to that is not add lots and lots of features. The answer should be add as few features as we need to stay relevant to the problems people want to solve and the hardware they want to run on, while respecting those core values of readability and simplicity. So we're never going to be the first kid on the block to adopt a new feature, and we're certainly not going to put in a feature without having a deep understanding not only of how it fits in with all of the other features in the language, but having spent a lot of time perhaps gazing into the crystal ball about how might it interact with a universe of possible future features. And that's not easy, and it's not something that happens on a predictable timescale, but language features are forever, and so we're going to choose them very, very carefully. So, as Mark said, the prime directive is compatibility. Java is successful today because code written 20 years ago just works. And this is about keeping our promises to the users, and this makes things take longer, and that's okay. It constrains our options. There are things we can't do for reasons of either code compatibility or, as Mark said, intellectual compatibility. There are features that we have rejected simply because that's not how Java developers have been trained to think over the last 20 years, and it's not worth trying to get them to change their thinking for the benefit. The cost is too great for the benefit. And so, we care not only about compatibility, we care about migration. Mark raised the example of generics. When you generify, you have a choice, of generifying a class now, later, or never. And there's graceful degradation at the boundary between generic code and non-generic code. And that was probably like 80% of the work of doing generics, was achieving that. So when people ask, why does everything take so long? It's because you wouldn't want the thing you would get if we did it faster. The same thing was true with lambdas, right? You had existing 20-year-old libraries that used single method interfaces for behavioral abstraction, and they just worked with lambdas without being recompiled. It was great, right? So, first, do no harm. Language features are forever, and each language feature has the potential to interact with every other language feature. So we have to pick carefully. And again, as Mark alluded to, if you don't know what to do, there's a right answer: do nothing, and hope that in the future you're smarter and you know what the right answer is then. This happened with generics. In 1995. We knew Java needed generics. It's not like parametric polymorphism wasn't understood at the time, but we also knew that the ways that we could have done parametric polymorphism in 1995 were not what we wanted. And I think we're all glad we didn't get C++ templates in 1995. And that, may make it worth having waited 10 years. The same thing was true with lambdas. There was a vibrant debate in the community around 2005 about how to add lambdas to Java. And it was actually pretty ugly, if those of you, any of you remember it. But it had to happen. It was important that it happened. And boy, am I glad we didn't implement any of those proposals. I think, what we implemented is better than those proposals, in part because we learned from those proposals. We looked at them, we thought about what was good about them, how to integrate their best parts, and I think we did pretty well. It took a long time, it was hard, but, that's what we do. And this is true, the way we look at things is true both for big language features and for small language features. So in Java 5 we did generics, that was huge. And in Java 8 we did lambdas, and that was huge. And in Java 9 we did modules, and that was huge. These were big features. So why did we pick these features? We picked them because we had recognized that these are pain points that developers are ubiquitously experiencing. The lack of data abstraction was a serious productivity problem in the early years of Java. And generics gave us a powerful tool for reducing the complexity. The lack of behavioral abstraction, same thing. Lambdas gave us a powerful tool for managing that complexity. And sometimes we do small features, like we did try with resources in Java 7, but they all have the same goal, which goes back to our principles: making it easier to build and maintain reliable code. That's what it's about. And that's why people continue to use Java, because they trust it, because the investment that they've made is preserved. So, some of the stuff we do is big, some of the stuff we do is small. We're actually doing more smaller stuff now because of the more rapid cadence, which I think is a good thing. I think we had probably over-rotated towards big things when we had a cycle of major releases every 3 years or so. But, whether what we're working on is big or small, the goal is the same: making it easy to build and maintain reliable programs. So I keep using the word evolve because I think that's really what's happening. Programming languages exist in an ecosystem, and when that ecosystem changes, you either have to evolve or you're going to die. And it's obvious there's no perfect programming language. And even if there was a perfect programming language for right now at this point in history, tomorrow it no longer be perfect, because the problems that we want to solve, the hardware we run on, and the rest of the state of computing is going to change. And so a tool that might be perfect relative to one set of conditions and problems is not going to be perfect tomorrow. So evolution is necessary. And you can sort of think of this as, in this environment, you have programming language and tools are kind of like the predators, and the problems we're trying to solve with programs are the food supply, and the state of computing hardware and infrastructure is sort of the environment we live in. And so rather than talk about language as being good or bad, I think it's better to talk about them being evolutionarily fit or not, because that's what's going to determine whether it continues to be useful. And the food supply changes over time, the environment changes over time, and some creatures adapt and some creatures die out. And we want Java to be around for a long time. So as a cautionary tale, think about what happened to COBOL. And we like to joke about COBOL, but COBOL was a seriously evolutionarily fit predator for the programming problems of the 1960s. Now, what were those problems? They were about, producing accounting statements, from databases stored on 80-column punch cards, and later magnetic tapes that emulated punch cards. But COBOL died out not because its food supply ran out. We still run these reports today. But a better tool emerged, SQL databases, and we didn't need a bespoke programming language for writing these reports when we could do them with better tools. Developer expectations changed too, and this is also part of our ecosystem. Java 1.0 didn't have generics, and a lot of us grew to like Java even despite that, right? How many people have started programming in Java back in the 1.0 or 1.1 days? It was pretty good, right? Yeah, I mean, we liked it enough that we kept using it. But now, if you go back and look at some pre-generic or pre-lambda code, who wants to program with that language anymore? No hands? Yeah, I don't. Yeah, it's always one. So, you look back at that code and you say, yuck, how did we live with that, right? But at the time, we thought it was pretty cool. Evolution is an imperative. So, all this is to say we're not done evolving Java. Java needs to continue to evolve, to adapt to new problems in hardware and new expectations. And we'll never be done, but we also have to be aware that it's possible for a language to get full, which is to say there's so much in it that it's impossible to cram anything else in without a big crowbar. And we would like to avoid getting full, so we have to pick and choose carefully. So let me talk about the major language-relevant initiatives that we're working on now. This is, this is some of the things that we think are important enough to put resources on. And again, these are all chosen based on listening to the community, listening to people's pain points, listening to the things that people have trouble with, that are error-prone, performance issues, et cetera. So Project Amber, which is largely about adapting to developer expectations. This is language changes for, you could call it reducing ceremony, you could call it modernizing the language. There's certainly a need for some of that. We try not to go overboard on this stuff because we don't want to starve out some of the bigger, more important long-term features, but it is important for the language to modernize. Project Valhalla, this has been going on for probably 5 years or so, and we're actually at the point now where we've delivered, I think, the first usable prototype, so things take a while, but it's going really well. This is about adapting to modern hardware. Hardware has changed tremendously in the last 25 years, and our solution to that is for the VM to support values as aggregates, to make data layouts in memory denser and flatter. And that sounds really simple. Why did it take so long? But that bubbles up through everything, and it's a big project. And the other one that's a relative newcomer that you might have seen the talk on Monday is Project Loom, which is about adapting to rising scale expectations. This is continuations and coroutines for the JVM, and this is making amazing progress. So these are some of the things that we've got going on. I'm going to talk about them individually a little bit. So one of the biggest complaints about Java is too much ceremony, and I think everyone knows what we mean, and there's an infinite number of proposed features aimed at reducing this ceremony, which means we're going to implement exactly 0% of that, and infinity is big. So we have to prioritize, right? So how do we prioritize? We prioritize going back to our principles, encouraging clear, readable code, eliminating places for bugs to hide. And a useful principle here is the principle of commensurate effort. Easy things should be easy, hard things should be possible. A lot of the suggestions we get are about concision. Oh, I could write this with much less code if you just let me do this. And I get that. I don't like writing more code than I have to either, but concision isn't a goal unto itself. And so our focus is a more indirect route to get to concision through better semantics. If you give people the semantics they need to express what they want to say, very often the boilerplate takes care of itself. So Project Amber has already launched. It's already delivered several features. We delivered local variable type inference in Java 10, and we've got 2 features that are spooling up on the runway that we intend to propose as preview features in Java 12, raw string literals and expression switch, and we've got more features in the pipeline, which I'll talk about. I'll just go through some of them really briefly. Most of you have seen these. Local variable type inference is extending type inference to local variable declarations, so instead of having to manifestly type every local variable, it can be inferred from the type of the initializer. This is not a rocket science feature. It's not as easy as it sounds, but it's not rocket science. But this was the #1 feature request that we got from developers who would buttonhole us at conferences. The one thing they asked for, because they had seen it in C# or Scala and really loved it, and said, it's a good fit for Java. I want it in Java too, and they were right. And so we did it largely because people were asking for it, and it was something that had already been proven to be a reasonable, reliable feature in languages that were similar to Java. Some people, there's always a tension. A lot of people complained, oh, this feature will kill Java because it's making code less readable. And it's actually a lot more complex than that. I think it's making some code more readable and some code less readable. If you pick good variable names, it's going to make your code more readable. If you pick lousy variable names, it's going to make your code more cryptic. We can't stop people from writing bad code. There's just too many bad programmers out there, not enough of us. But it's a tool that responsible programmers can use to write better code. Frequently the variable name is more informative than the type name, and bringing that front and center can make the code more readable. So not a big feature, but something we did because people were asking for it. The 2 smaller features that are warming up on the runway are raw string literals. So string literals in Java are kind of a mess to program with. You have escape characters, they're limited to single lines, and that means coding things like regular expressions or Windows file paths are really painful, and embedding snippets of JSON or HTML in Java is kind of painful. But it's not the pain directly that we're actually so concerned about, it's the error-prone part. That if you have to, if you copy and paste something into your Java program and then have to mangle it up with escape characters and such, that's error prone. That's making the code harder to read, and we care about that a lot. So simple syntactic change to allow you to, instead of having to manually concatenate strings and escape new lines, to allow you to express strings that span lines and that have strange characters in them more directly, means that things like snippets of HTML or Windows paths or regular expressions or embedded queries are just a lot simpler. So again, not a rocket science feature, but also was very high on the list of things that people asked for over and over again, and we do listen. A more fundamental feature that we're going to be previewing in 12 is expression switches. And this is, again, about readability and error proneness. So a lot of switch statements really want to be expressions, but we didn't have a way to do that, so what people do is they work around it by having a switch where in every arm you assign to some common variable. That results in something that is kind of verbose. You have to say break at the end of every block. People can forget that. That makes it error prone. And there's a lot of repetition here. I'm assigning to the same thing in every arm. And it's also error prone. I could forget to assign one of these arms, and I might not get caught by definite assignment. And so we basically gave people the wrong tool. They had to work around the limitations of the tool, and it was error prone. So if you allow switch to be an expression, you can rewrite this as this, which is much shorter, and people like that. That's the concision people want, but it's a lot more clear, and it's a lot less error prone. You can't forget to break. You can't forget to cover all the cases. And so the compiler works with you to validate your assumptions rather than you having to bake those back into your program. Okay, so that's another example of the kind of feature that we're working on to make ordinary, everyday code more reliable. Again, not rocket science, but still worth doing. So some other features that are in progress in Project Amber, and this is only a partial list, and the order in which we do them is changing every day. Records, pattern matching, intrinsics for allowing you to express invoke dynamic directly in Java. This has been like a 10-year-old request ever since we did JSR 292. Sealed types and improvements to serialization. And a lot of these features actually do work with each other, and the expression switch feature actually sedimented out of the pattern matching work, where we started working on a bigger feature, which was pattern matching, part of which was improvements to switch, and then we realized, okay, well, pattern matching is a big thing, but the improvements to switch, those are ready. Let's factor them out. They can benefit people immediately, and then we'll keep working on the bigger thing. Okay, so I'll blow through these pretty quickly because the goal here is just to sort of see the kinds of things that we're working on and the kinds of things we're thinking about when we evolve the platform. So, biggest boilerplate offender in Java is modeling data with classes. Many of the classes that people write every day are just dumb holders for data. And so you have a lot of boilerplate, and the common thread of all that boilerplate is where does state meet API. So that includes constructors, accessors, equal, hash code, etc. And that's annoying boilerplate to write, although the IDE will write it for you. It's annoying to read, the IDE won't read it for you. But the bigger problem is this is repetition. Repetition is a place for bugs to hide. And so we don't want to put people in this situation where they have to write error-prone code. So, we'd kind of like to write our point class like this, but that's not actually what the point class looks like. The point class looks like this. And again, that's a lot of code, and even if the IDE generates it all, which it did, you have to read it to make sure that there's nothing special in there. And then you go to change it, and you update the equals method but not the hash code method. Oops, and now you've got a subtle bug, right? And the reason for that is people are expressing things at the wrong level of abstraction. So we would like, to make it easier to say what you mean. If you want a data holder class for a particular state vector, you should say that, right? So one way we might write that is this. Instead of saying class, maybe we'll say record. Maybe we'll call it data class. Scala calls it case class. The syntax doesn't matter, but the concept is common to a lot of languages. And this gives us the boilerplate reduction that most users are asking for, but it's not really about boilerplate. It's about making a stronger semantic statement of this class is just a carrier for its data. And by making that semantic commitment, then the compiler can infer all the garbage for you because they flow from the semantic statement that you've made. So general theme here, focusing on semantics, the boilerplate takes care of itself. So a lot of the suggestions we get for language features are largely focused at boilerplate. We largely ignore the proposed solutions, and we look at the underlying problems that they're trying to solve, and then we try to distill out, is there a broader thing we can do that solves that underlying problem? Now, this looks like a trivial feature, and some of you are probably wondering, hey, Brian, you've been talking about this for a year and a half now. Why haven't we seen it yet? And that's not because I'm lazy. It's because the boundaries of this feature are not yet well defined enough to our satisfaction. There's an awful lot of almost cases where users are going to be frustrated, where they almost can make the semantic restriction to fit into a record, but they can't quite, and then they fall off the cliff, and they have to go back to the old horrible way, and then they're angry at us. And then they distort their code to try to fit it into records when it isn't really a good semantic match, and now their code is, again, error-prone. And so, we have this tension of we'd like to make it applicable in more places so that more people get the benefit of it, but if you weaken it too much, you're giving up on the semantics that derived, from which you derive the benefits, and that helps no one in the long run. It's a Band-Aid. So what we've realized in the course of thinking about this feature, and this is often how it goes, is you start out with an idea of oh, we'll just do this, and you realize that you're solving the problem at the wrong level. Really, this is a set of a number of smaller features having to do with better constructors and a better way to talk about accessors and a better way to talk about equal equals and hash code and toString. And so we are now iterating on our design of what are those underlying features that this feature is really approximating so that we can deliver those more directly. So work in progress, and we've had great input from the community on this. We have an active expert group for Amber that has been really helpful in guiding our thoughts here. Okay, let's talk about a few more features. This is a somewhat bigger one. This is actually kind of where we started with and a number of the other features I've talked to already have kind of sedimented out of this bigger goal. That's often how it goes. And one of the benefits of the more rapid cadence is we can do that. We can deliver pieces of it when we realize that they're in good shape. So pattern matching is a concept from a lot of, that's present in a lot of functional languages, although it's not strictly a functional programming thing. And it's really just a simple matter of combining several things that we do all the time in our programs anyway. Combining a test, are you a foo, with an extraction, a conditional extraction. If you are a foo, cast it to foo and get out the X field of foo, and binding those results into variables. So we write code like this all the time, but we do it as three separate things, and that involves a certain amount of repetition and therefore a certain amount of error proneness, and we hate that. So as an example, here's a snippet of code that some of us have written too many times, where you have some object that you don't know its dynamic type. Your static type is just object or some interface, and so you do a bunch of instance of tests. Is it an instance of this? If so, cast it to this and do that with it. Is it an instance of the other thing? Repeat. And there is a boatload of repetition here, right? Look how many times we're saying, is the same thing an instance of some type? We said, are you an instance of integer? And then what's the next thing we do? We cast it to integer. What else could we possibly do next, right? Why do we have to say two things here? And then when we're acting on the result, we're, again, repeating the assignment to a common result, right? So this is all repetition. This is all place for bugs to hide. We write code like this all the time. This code should be a lot clearer, a lot more readable, a lot more simple. So pattern matching gives us a way to do that. Pattern matching allows us to combine the conditional test, the cast, and the binding of the variable into one go. So here's what this code looks like using pattern matching. We have a slightly refined case label, which has a pattern. These are type patterns. A type pattern is applicable if the thing is of that type. And if it is of that type, it casts it to that type and binds it to the variable whose name follows the type. So all of a sudden, a lot of the garbage has gone away, but there's still a lot of repetition. We can apply the previous feature I talked about, expression switches, to represent this code as an expression switch. And when you do that, you have an expression switch whose case labels are patterns. This is kind of the code you had in your head when you were starting to write that thing in the first place. But you couldn't write the code you wanted to write. You had to write the horrible code. And as a result, it was hard to read and it was error prone. Right? So a lot of what we do in language evolution is looking at the patterns of code people write over and over again and say, what's wrong with that code? Why is that code not desirable? Is there a better way to express these very common operations? So, okay, pattern matching is cool. We've done quite a lot of things so far. We generalized switch, we added type test patterns, but it's actually a feature that has a tremendous amount of depth, and it's something that we'll release in stages. But I think it's a good example of a feature that has both, that has multiple layers to it. It's not just add this thing and then move on to another thing. It's committing to a direction that will yield dividends over a long period of time. So here's an example of taking pattern matching a lot farther. So I talked about records. One of the things about saying I'm a data holder for this vector of data means that not only do you get constructor and accessor and equals for free, but you also should be able to reverse construction. You know what the fields are. And so we can roll that into our pattern matching story. So I know I'm going through this quickly, but it gives you an idea of how we can improve code that would otherwise take many, many more lines of code. So I've got a record point. I've got a type shape. And I have two subtypes of shape, circle and rectangle. And I've said, and these are the only two types by marking the interface sealed. That's another feature that's in the pipeline. And what's a circle? Well, it has a center and a radius, and a rectangle has a lower left and an upper right corner, and I want to compute the area of these things. Okay, well, I can do that. I can do that by switching over these deconstruction patterns. What do those deconstruction patterns mean? Well, the pattern circle var C var R means it matches when the thing is a circle. If it is, it casts it to a circle. It extracts the field, center, and radius and binds them to the variables C and R, which I can then use in the expression on the right side of the arrow to compute pi r squared. And similarly, if I have a rectangle, and I say case rectangle, and it binds the lower left, upper right points, and I compute delta y times delta x, and I get the area of the rectangle. Now, doing this without pattern matching and without records would be a lot more code. And a lot of that code would be more repetitious, more error-prone. This brings the calculation that you want to do. If it's a circle, compute pi r squared. If it's a rectangle, compute delta y times delta x. Brings that code front and center. Fewer places for code for bugs to hide. Makes code more readable. This rabbit hole actually goes a lot deeper. Those var C and var R are actually not declarations. They themselves are patterns. They just happen to be patterns that match everything and bind whatever their target is to the variable. But if we wanted to have a special case for a rectangle whose point was the origin, well, the thing in the first subpattern in case rectangle is exactly that. That matches a rectangle whose lower left matches point 0, 0. And so if we match that sort of more refined point, we have an optimized calculation we can do. And if not, we just go on to the next one and we match the more general point. So this is a feature that has a lot of depth. If you look at what you try to do in Java without this, we end up writing visitor pattern. How many people here use visitor pattern? How many people love visitor pattern? Visitor pattern sucks. The only good thing about visitor pattern is it works. That's it. It's solely a workaround for the fact that your language doesn't have pattern matching in the first place. And this code with visitor would be 5 times as long and more brittle. So, okay. Last thing I want to make about pattern matching, because this really is a deep rabbit hole. We've actually been working around the lack of this in the language for years and didn't know it. We write APIs, like here's an example of, from the class API. We have a pair of methods in JavaLang class, isArray and component type. What does component type do? Well, if the class describes an array, it extracts the component type. And if it doesn't describe an array, then you made a mistake. So this is an error-prone API. You can call that method on something that isn't an array, and it does something. Maybe it returns null, maybe it throws an exception. The fact that, like, I don't happen to know immediately off the top of my head is already a sign of what the problem is. It's more work to write that API, because you have to specify the error conditions, and it's possible to use that API incorrectly by calling component type without calling isArray. If instead we said, recognized these two things are coupled, you really can't call one without the other. Let's expose those as one pattern called array class. And you would invoke it by saying, if my class is an instance of array class var component type, now I can't call it incorrectly. Either it says false, or it succeeds and I get the binding in one go. So as API designers, we've been working around the lack of this and didn't even notice it, right? But there are a lot of APIs that would be much better designed this way if the language had this feature. Okay, moving on to some other features, targeted compiler intrinsics. The best way from a readability perspective to implement toString is using string.format. From a performance perspective, that's not a very good way to implement toString. Putting developers in that position where they have to choose between readability and performance is a bad deal. It's asking too much of developers. Why is it slow? Well, we box primitives into objects, we box the arguments into a var-args array, and then we reinterpret the format string every time, even though it usually never changes. So people don't use it. People say, oh, don't use string.format, it's too slow. We've been working on compiler intrinsic for this. With a little bit of code in the compiler, we can get, significant performance improvement on the order of 30, 40x, so that it's actually competitive with the performance of string concat. And you might say, oh, cool performance hack, and it is a cool performance hack, but it's not motivated as a performance hack. It's motivated to encourage people to write the code they should write in the first place by removing the fear that the right way is too slow. Okay, so that's Project Amber, or part of it. Covers a pretty broad range, but it stays within the theme about building and maintaining reliable programs. A lot of them address long-standing pain points. Some of them are deeper features, some of them are not so deep. But by eliminating needless repetition, we eliminate places for bugs to hide. We make Java code in the aggregate more reliable. And one of the big differences between a developer and a language steward is a developer mostly cares about their code. A language steward cares about everybody's code, right? People come to me and they complain and say, I don't want to have to write this. And I understand their pain, but really what I want, I'm optimizing for all the Java code out there. And I think that's a better investment of our language design bandwidth. Okay, so the other project I want to talk about, and I think John will probably talk about this some more, is Project Valhalla, which aims at rebooting the layout of data in memory. Okay, sounds cool. Why? Well, hardware has changed. 30 years ago, the cost of a memory fetch and the cost of an addition were about the same. In those 25 years, hardware has changed a lot. And the relative cost of a memory fetch versus an arithmetic operation is now like a few hundred to 1,000x difference in the worst case. And it stands to reason that let's just stipulate that what we did in 1995 was absolutely perfect. Absolutely right thing for the hardware of the day. Well, it's not right anymore. Might have been wrong then. It's unlikely it was exactly wrong enough then to be right now. So whatever we did then was good for then. We need something else for now. And the big culprit is pointer indirections. Pointer indirections are hazardous to performance. And why are Java data structures so pointery? Because everything is an object and all objects have identity. And that was a sensible part of the religion in 1995. But what we realize is that not all objects need polymorphism and mutability and locking and all of the other things that object identity serves. So why should they all pay for it? So when we lay out, say, an array of points. We have our point class, should be a record, and we have an array which is an object with an object header. The dark blue is the object header, and it has some elements, and the elements are references to other objects, and those other objects have headers. So what's going on here? Well, we have a lot of objects. That's work for the allocator. We have pointer fetches to traverse when we try to go fetch those XY values, and that means cache misses. And we have all those object headers, which means more memory has been allocated. And, to work around this, sometimes developers will write code like this, and they'll shred their array into two arrays. How many people here have done this trick? How many people are embarrassed that they've done this trick? You all should be embarrassed, right? We have to do it sometimes, but it's disgusting, and it is error-prone, right? It leads to bad code. Sometimes we have to write bad code in order to meet our performance requirements, but we shouldn't ever be proud of it. And, we would like to not put people in a situation where they have to choose between good code and performant code. What most developers, would like in this case is to get this memory layout, where I have an array of points, and the array contains XY, 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 right? So the question is, what do we have to do to get this layout in memory? And, the answer is value types. A value type is like an object in that it has, fields and methods and things that objects have, but its memory behavior is like that of a primitive. And so they can be flattened into other objects, they can be flattened into arrays, they can be treated as values. And surely not all classes want to be values, but surely a lot of them do. Things like numerics that don't fit into the 8 primitive types that the JVM gives you. Things like cursors into data structures. There's all kinds of things that pop up all the time, everyday programming, that are nominally values. So, the motivation here is quite simple. Master Yoda tells us that identity leads to pointers, pointers leads to indirection, and indirection leads to suffering. So what's a value type? It's a pure data aggregate, just its data, no identity. It is its data. You compare two values, you're comparing not their pointers, but their data. So what do we give up for this? Well, we give up representational polymorphism. You can't have non-trivial superclasses. We give up mutability. That's okay. I don't need to modify the complex number 0, 0 very often. We give up nullability most of the time, and that's a little bit of a tricky one, and there's a lot of work going on to refine what that little asterisk means. And by giving up on these things, which sometimes we're willing to and sometimes we're not, we get routine flattening. Flattened into arrays, flattened into other values, flattened into other objects, no object header needed, and aggregates that have the runtime behavior of primitives. You can pass them in registers, you can pass them on the stack, rather than having to allocate them on the heap and take pointer interactions. But unlike primitives, they have a lot of cool stuff. They have methods, they have fields, they can implement interfaces, they can use encapsulation, they can have private fields, they can use generics, they can have type variables. So the general rule for understanding how value types behave is to ask, what would int do, right? So for example, what happens when you assign a value to object? Well, what happens when you assign int to object? It gets boxed, right? So, you could equally describe value types as either faster objects with restrictions or user-defined primitives, primitives with fields and methods and encapsulation, and kind of like the war cry is codes like a class works like an int. And again, like I said, not all our classes will become values, but the ones that do, we will be very happy for. The machine learning folks will be very happy about this, for example. A lot of applications. In fact, who wants value types? I think everybody wants value types. Application writers who want to reason about footprint and locality of data-intensive code. Library writers who want to write more efficient hash maps or more efficient algebraic data types or numerics or cursors, more efficient collections. Library writers are really going to groove on this. Compiler writers will like this because value types are a good substrate for a lot of language features that you want to implement, like tuples. If you have value types in your underlying platform, then implementing tuples is a very straightforward thing that you can do on top of values. So I think, even though this sounds a little esoteric the way I describe it, I think almost everybody will come around to realizing there's a place for values in their toolbox. Okay, so geez, Brian, you've been talking about this for 5 or 6 years now. Why is this taking so long? Why is this so complicated? It really sounds simple, doesn't it? It's very deeply intrusive. It intrudes into every layer, all the way down to the VM. New type signatures, new bytecodes, new semantics, new language features, interacts with generics and wildcards and nullity and then there's the libraries, right? It's like we could do all the work in the VM and the language, and now, well, we want to make our libraries value friendly, and that involves changes to collections and streams, to take advantage of this. So it's a small feature that's connected to every other feature. And if you pull on that string a little bit, the next obvious question is, well, what about generics over values? Right now we can express generics over primitives with boxing, and we get the exact same horrible memory layout I drew a picture of a few slides ago. So you could say array list of integer and express what the user needs, but it's not the performance the user wants. So for all the same reasons we want values, we want to be able to abstract over those with our data abstraction tool of choice, which is generics. We want to be able to say array list of int or array list of value and have it be backed by a real flattened array of ints or values. As someone who's written a lot of APIs, I have to tell you, dealing with boxing is a huge distortion in the API design process. And so, we design APIs and then, we look at the natural way to express them and then we say, oh God, but this is going to get boxed and that's going to get boxed and it's going to perform terribly and the users aren't going to like it. And it becomes a distorting impact on the design of our APIs. And boy, am I looking forward to not having to deal with that. When we did streams, we were forced to do manual specializations of in-stream and double-stream because the performance was going to suck otherwise. And that was such pain and such constraint, and it would be nice to be rid of that. So, this is very much a, looking at the pain that we've gone through in other library projects, other language projects, and realizing, boy, if we had this 20 years ago, it would all have been so much easier. Okay, specialized generics. If you're generifying over a broader range of types, the set of things you can actually do is reduced. So for example, if you're generifying over both references and values are not nullable, then you can't assign things like null to a, to a type variable. So this intrudes on the generics language feature. Not sure exactly what it's going to look like. Maybe it looks like this, maybe it doesn't. But you'll notice instead of saying this.t equal null, I'm saying this.t equal t.default. Give me the default value for whatever t is. And so in order to extend generics to support generics over values, we're going to have to do some work. And again, we're going to do the same trick we did with generics in the first place. We're going to allow gradual migration compatibility so that no one is forced to generify on day one. But if you generify, the generic and non-generic or old generic and new generic code will interoperate gracefully, and you can migrate your code base gradually. So, the trick the trick and the pain we went through with generics, we're going to have to go through all of that again. And like I said, probably 80% of the work in generics was managing migration compatibility. A big fraction of the work in modules was managing migration compatibility. A lot of the same work is present in this project too. So, okay, you could say that Valhalla is about performance, making object graphs denser and flatter, so we get fewer headers and fewer indirections, and that's true. So you could think of them as faster objects, and you could think of generics over values as faster generics, and that's all good. Or you could think of this as being about abstraction. You could think about it as caulking the seam between primitives and reference types, so that you can write one generic class that generifies over everything, generifies over objects, over primitives, and over values, and maybe even over void, so that we can write things once rather than having to write it n+1 times. Have any of you ever peeked into the arrays class, Java util arrays? So we have things like arrays.sort, and there's like 9x copies of each method. We would like to get away from that. We would like to be able to use generics as our tool for abstracting over primitives and values as well. But the underlying goal here is stop making users choose between performance and abstraction, because they're probably going to choose wrong. So if we eliminate the temptation to hand unroll objects into primitives or hand roll primitive specializations, people can just write the sensible code that's readable, and it'll also be fast. And that's what winning looks like, right? So, okay, so status. Last year, we released a prototype called Minimal Value Types. It was truly minimal. It was really, really hard to use. It was basically a proof of concept that represented the result of the first 3 rounds of experimental prototypes internally. We've just released our second public prototype, which is actually the first usable public prototype, called L-World 1. It's named that for esoteric reasons. But the big change is that we're treating values as subtypes of objects. This is a bit of an experiment to see if it's going to work and see if it's going to perform well enough. Limited language support, but enough to write value types. So it's ready for early adopters, and this is part of a long story that's playing out. So one last project I want to allude to, but I'm not going to say very much about, is Project Loom, which is about continuations and fibers. So Java was the first mainstream language to have an integrated model for concurrency and an integrated memory model. And this was a huge, huge, huge step forward over the alternatives at the time. And it enabled like really powerful and efficient concurrency libraries like Doug Lee's Java Util Concurrent library to be written pretty much in pure Java code. But threads are pretty heavy. And today we have problems we want to solve where we're dealing with tens of thousands, hundreds of thousands of connections. And thread per connection is just too heavy for that. And the programming models that let you avoid thread per connection are pretty darn unpleasant and error prone. So exposing a lighter weight concurrency primitive will enable us to write code that's actually readable and maintainable and deal with the scale of tens of thousands of connections. So currently the focus of Loom is on the VM primitives, the language and library work about whether we expose fibers or coroutines, or how we expose them in the library. That's work that's coming in the future. But it is at a stage that people should get involved. And I think a lot of the people in this room work for companies that would very much like to see Loom succeed. And this is the time for people to get involved, make it happen faster. Summary. We plan to continue to evolve the Java language cautiously and deliberately, in conjunction with evolving the JVM, hopefully getting to a point where the whole is bigger than the sum of its parts. I think value types is a good example of that. One thing that I'm really happy about is our feature pipeline of things that we view to be possible and achievable in the near to intermediate term is better than it has ever been. There's so much exciting work going on, and a big part of this gathering this week is how do people get more involved. So I hope that all of you will be inspired by the things that I talked about and that John's going to talk about, and are going to say, I want to get involved in that, and we'll have ample time to talk about that in the rest of today and tomorrow. So thank you very much.